Welcome to the Oracle Class 311. More stories from the Secret City. This is July the 6th, 2026. Glad to have all of you here today. And we have as our guest Jim Roberto, who's going to talk to us about Tennessine. But I want to recognize, and I don't see him on here, the person that suggested this to me. Uh, Wait a minute. People are still coming on, so let them in. We were at I think the State of the Lab presentation at the American Museum of Science and Energy. And this gentleman came up to me and said, I've got an idea for your Oracle class. And I said, okay, what is it? I'm always looking for ideas, as you all know, who've been on here before. I ask you to give me input for what you'd like to see addressed in the coming weeks of the program. We'll be on here 3 Mondays in a row. And he said, I think you ought to have Jim Roberto tell the story of how Tennessine came to be. And I said, okay, we'll do that. So that's where we are, and that's what's going to happen today. Now, as I always do, I encourage you and thank you for muting yourself. But if you want to ask a question, even though Jim's going to be putting up slides and he's going to be talking like it's a presentation, and it is, if you interrupt and just raise your voice and ask a question, he'll stop and deal with your question. And we'd much rather do that than just have the presentation. But it's up to you whether you want to do that or not. Another thing you can do if you don't want to interrupt with a voice, if you'll send a chat, I'll monitor the chat and I'll find a place to come in and and make the question, give the question to Jim. So you have two ways that you can get your input. And then, of course, we'll have some time for discussion at the end as well. So now I want to say one other thing. If you're looking at at your screen and you see all of the pictures of us over on the side, if you'll go up to the top of that, you'll find that there are some options for how that is displayed. And if you'll go to the left-hand option, the one that's the most left-hand one, it's just a little line. If you click on that, it'll make it really small. Then you can put your mouse on it and you can move it. And that way you'll get it out of the way of the words on some of these slides. So that's an option to make it easier for you to see the information that Jim's going to be presenting to us. Jim, have I covered everything
You
we
have.
talked about doing? All right.
Yes.
I'll keep watching. Other people will still come on, and I'll bring them on as they come in. And we'll go ahead and get started then. So, Jim, take it
Okay.
away.
Well, thanks, Ray, and thank you for inviting me, and thank you to all of you for showing up. Uh, I really appreciate this opportunity to tell this story. And it's interesting because there were a number of Nobel Prizes that were involved. So not for our group specifically, but in areas of science that enabled the kind of work that we did to discover this new element. So we're going to start with Mendeleev and the periodic chart. We'll go through to the super heavy elements, which include Tennessine, and there will be a few Nobel Prizes along the way. Okay, Ray. No, so I'm trying to go
Yeah,
to the next slide. There,
there you go.
it works. Okay.
Yeah, you got it.
So early development of the periodic table, Manhattan Project years, the transuranics, which were essential to opening the door to the super heavies, and the first super heavy elements. That's basically the historical context. And then we'll talk a little bit about the actual synthesis of these elements, including the role of actinides, which was crucial, a crucial role that Oak Ridge plays, the hot fusion breakthrough, which enabled the periodic table to go from 113 to 118. International collaboration, none of this work could have been done without international collaboration. And I'm going to emphasize that a lot because that was key. And then, of course, the specific story of how Tennessine came about. And then we'll talk a little bit about superheavy element research today and where the field might be going. So in 1869, Mendeleev created the first modern periodic table. He did this by arranging the elements in a two-dimensional array according to chemical properties. This was actually an enormous insight because when he did that, he saw gaps in the periodic table. And those gaps actually suggested the possibility of 10 new elements, and 7 of them actually exist. So 50 years before many of these elements were discovered, Mendeleev predicted them based on his insight on how to arrange the periodic table. In 1906, Mendeleev came within one vote of winning the Nobel Prize for this work. It turns out that he died the following year, and the prize is not awarded posthumously, so he became ineligible, but he likely would have won the prize had he lived longer. In 1913, Henry Moseley at Manchester demonstrated the importance of atomic number in the periodic table. What he did was he excited various elements with electron beams and watched the characteristic X-ray spectra that were emitted. What he found was that the number of protons in the nucleus was the determining factor in the periodic law. And you can see kind of the linear tables here where all the elements line up when you plot the frequency of the emitted X-rays against the element. When he tried to do this by atomic weight, it didn't work. There were no straight lines. The plots were all over the map. And so this made it clear that it was the number of protons in the nucleus that determined the chemical properties of those atoms, which actually means the number of electrons, because the number of electrons is equal to the number of protons. By 1939, there were 91 known elements, ending with uranium, Z equals 92, atomic number 92. And element 61 was the only missing element in the original chart. Now, Moseley was working at Manchester during World War I. And he was a patriotic guy, and he enlisted in the British Army and served in Turkey during World War I. Unfortunately, he was killed by a sniper. He most likely would have won the Nobel Prize for this work had he survived World War I. During the Manhattan Project, the discoveries of plutonium, americium, and curium were achieved at Berkeley. This knowledge was withheld due to security concerns, obviously, particularly because of plutonium. So the periodic table that we see at the right in this chart was kept up to date and displayed in a secure area of Y12. It was actually showing classified information at that time. Promethium element 61 was also discovered at this time at Oak Ridge at the X10 graphite reactor. Uh, and because of security concerns, again, it was not announced until 1947. This periodic chart from the 1940s uh, is still can still be seen at Y12. So after the war, the Manhattan Project facilities were repurposed for early isotope research and production. These were unique opportunities in the world for that kind of work. And what we see in the top of this figure are the calutrons at the left and the face of the X10 reactor at the right. Following this repurposing, the first shipment of a radioisotope to a hospital for cancer research occurred in 1946 from Oak Ridge. By the 1960s, there were 100,000 shipments annually with applications in research, medicine, and industry. And today, there is significant new investment in stable and radioactive isotope capability to meet commercial, medical, and research needs. The picture at the bottom right shows the new stable isotope facility under construction at Oak Ridge today. It's going to be completed in a few years at a cost of about $300 million. And following that will be a new radioisotope capability that will probably cost about $400 million and will also be constructed at the lab. In the 1940s and 1950s, there was a lot of interest in moving beyond uranium to create the so-called transuranics. These elements beyond atomic number 92 do not naturally exist on Earth. Fermi, who was in Italy at the time, proposed creating these heavier elements by irradiating uranium with neutrons. In the process of doing this, he missed the discovery of fission. However, he did make sufficient progress on the understanding of nuclear physics that he was awarded the Nobel Prize in 1938. And he took that opportunity to take his family to Sweden and then moved on to the United States to escape Italy during World War II. Seaborg and his co-workers at Berkeley synthesized elements 93 through 103 in the 1940s and 50s, and for this work, he received the Nobel Prize in 1951. One of these elements was named Seaborgium in his honor, and he was the first individual to have an element named after himself while he was still living. There's an interesting story surrounding this because his adult daughter was driving at the time and heard on the radio that her father had an element named for him, and she mistakenly thought that he had died and pulled off the road and was able to sort it out. But that was the extent to which the belief was if you had an element named after you, you were no longer living. Now, it was complicated to accommodate these new elements in the existing periodic table because if you expanded the table to accommodate them, the table would have 32 rows instead of the present 18, and that can't fit on a single page. And so in the picture, you can see how he cut up the existing chart and created, the actinide series below the existing chart with the lanthanide series, and therefore was able to keep the 18 column format, but you had to have these two series below the existing chart. It turns out it doesn't matter how you do it. Either way is correct. And the current chart includes the lanthanide series and actinide series below the existing 18 columns. Seaborg also envisioned the existence of super heavy elements, those with Z greater than 103, uh, that would be part of a seventh row of the periodic table. That would be part of this, that would complete the seventh row of the periodic table. And that's where the focus of this talk is. So Seaborg realized the importance of the transuranics uh, and understanding their properties. And at the time, you could only make extremely small quantities. So he wrote a letter in 1957 to Louis Strauss uh, to propose a very high flux reactor for heavy actinide production. Now, it's interesting that this Louis Strauss is the same Strauss who uh, was a key player in denying Oppenheimer his security clearance. And so it's interesting that a great advocate for science also turned out to play, one of the notorious roles in science as well. So Seaborg argued that future progress in the field of the new transuranic elements requires production of substantial weighable quantities of berkelium, californium, and einsteinium. With Seaborg's support, Oak Ridge designed and constructed the high flux isotope reactor and the radiochemical engineering development center to produce these elements. And you can see the HIFER and the REDC just after construction was completed in 1966. 50 years later, these facilities are successfully operating and have enabled the discovery of new elements 114 through 118. The first super heavy elements, and these are elements with atomic numbers 104 and higher, were actually discovered by heavy ion bombardment of actinides at Berkeley and in Russia. These elements would not exist without quantum effects because the Coulomb or the repulsive forces of having a huge number of protons in a nucleus would cause them to fly apart. And so this is a very early indication of the real importance of quantum effects in nuclear physics. These were placed in the seventh row. You can see uh, of the periodic table, and you can see after you add the lanthanide and actinide series, you go back to the original organization, and that seventh row is the row that we are currently completing of the periodic chart. So modern theories of nuclear structure predict the existence of an island of stability for super heavy elements. What this means is they'll live long enough that you can study them. Now, you may recall from high school chemistry that atoms with closed shells of electrons, like the noble gases, are very stable. Well, it turns out that nuclei have shells as well, shells of both neutrons and protons, and the nuclei with closed shells have stronger binding. This was originally discovered by Gebert Mayer and others in 1949, for which they received the Nobel Prize. Wigner also shared in that prize uh, in 1963. So the heaviest stable isotope in the current periodic chart is lead-208, and it has closed shells of both neutrons and protons. So let's imagine that, I mean, we can calculate now based on this shell theory where the next spherical closed shells would be. And this would be for atomic numbers around 114 and neutron numbers around 184. So the question is, can we get there? And if we can get there, what will the lifetimes be? Some theories suggest exceptionally long lifetimes, maybe years or more, uh, in the region of this next predicted closed shell. The term island of stability was actually coined by John Wheeler for this region. So what we're actually doing in these super heavy element studies is we're on a journey to explore the island of stability, to discover atoms and nuclei beyond the known nuclear chart. In the 1980s and 1990s, uh, a new breakthrough called cold fusion uh, uh, was uh, was uh, enacted at the GSI lab in Germany. And the idea here was to bombard a heavy target, lead or bismuth, with a heavy ion, like iron, nickel. Uh, this has allowed the periodic table to be expanded to Z equals 112. But you can see from the chart that as you go to higher atomic numbers, the cross sections get lower and lower. And by the time you get to element 113, which was discovered in Japan and named nihonium, you were down to one atom a year or less. You can't run a research program at one atom a year, uh, and particularly if the next element might be one atom every 10 years. And so at this point, we didn't know what to do. It wasn't me, but the science did not know what to do, did not know what the future of the periodic table was, uh, because there was no clear path to go forward. But in the 2000s, a breakthrough called hot fusion uh, was developed in Russia. Uh, in this case, we bombard actinides like curium, berkelium, and californium, the actinides that are produced at Haifa, with calcium-48 ions to create a compound nucleus with excess neutrons. Calcium-48 is a special isotope of calcium uh, with a relatively low abundance, but has extra neutrons. These neutrons help stabilize uh, super super heavy elements uh, that are created by combining the calcium 48 with the actinide target uh, by taking off some of the excess excitation energy by neutron emission. And the result is that you lower the probability of the compound nucleus to fly apart because of fission. The cross sections increase sometimes by 2 orders of magnitude, and this allowed extending the experimental reach to Z equals 118. Now, Oganesson at Russia, at the Joint Institute for Nuclear Research, worked for Georgy Flerov. And Flerov is the person in Russia who wrote the equivalent of the Einstein letter for the Russian atomic bomb. And Yuri was away for several months. Flerov was away for several months, and that allowed Yuri to do experiments to demonstrate hot fusion. Flerov had told him not to do it, to work on other things. So fortunately, it worked, and Yuri didn't get fired. But this has enabled the periodic table to be expanded to Z equals 118. And you can see from the chart the red bump in the chart are those new elements and increased cross sections for hot fusion, which made all of the difference and allowed the periodic table to be extended. Unfortunately, above Z equals 118, calcium 48 no long, is no is no longer useful because you need targets heavier than we are currently capable of making. And so the result is we're at an impasse again at Z equals 118, and we're looking for new ways to go the next few atomic numbers. So why actinide targets? Well, they're closer in Z to the element being synthesized, and the reactions are asymmetric, which means that the product of the atomic numbers of the beam particle and the target is lower, and this means you have lower Coulomb forces. The actinide targets also have the highest N, so you have this ability to enhance stability of compound nuclei because you have a higher fission barrier, and because excitation energy can be reduced by the emission of these extra neutrons. So calcium 48 can be used with actinide targets to produce these super heavy nuclei with large numbers of excess neutrons. Berkelium 48 is the target for element 117, californium 249 for element 118. And as we said, Z equals 118 is the upper limit for hot fusion. And so we have to start looking at additional approaches. So actinide targets, which are again a product of HIFER, have transformed the periodic table 19 new elements beyond uranium since 1940, 8 new super heavy elements since 1964. The 5 most recent uh, element 114 through 118 have depended on heavy actinides with calcium 48 beams. Uh, and the ongoing and planned new element searches uh, are also going to be dependent on heavy actinide targets, uh, but probably with beams heavier than calcium 48. So these targets have enabled exploration of the island of stability, including the discovery of new super heavy elements. So as we have said, hot fusion has resulted in 5 new elements since 2000. You can see them here, uh, fluorinium through oganesson, the nuclei, and you can also see the number of nuclei that were uh, made in each of these experiments. So the numbers are relatively low. But in this process, we created 50 new isotopes, 300 new decay chains, and and obviously Yuri Oganessian's approach of hot fusion significantly increased the ability to have these discoveries. Now, it's interesting. You may have noticed that element 118 was named oganesson. This was done by the discovery team in Russia and in the US, where when when you when the International Union of Pure and Applied Chemistry accepts your proposal for a new element, and that acceptance takes a long time. In our case, it took about six years. They invite the team to propose names. Uh, and we proposed for element 118, we asked Oganessian to leave the room, and as a group, we proposed to name element 118 for him. And the International Union accepted that, and he is the second living person to have an element named after him. During that meeting, we also proposed Tennessine for element 117, and element 115 was discovered at the same time. We proposed Muscovium. Those names representing the regions where contributions to the discovery were made. So this is the periodic chart in 2009. And the gap you can see is 117. So international collaboration was essential in filling that gap. And this is what it took to produce a few atoms of element 117. You had to take natural calcium 48 and enrich it 500 times to natural calcium and enrich it 500 times to have the source for a beam of calcium 48 ions. This was done in Russia uh, in some of their research complex for nuclear weapons. We had in Oak Ridge, we had the unique capability to produce berkelium 249. And this was uh, created at the high flux isotope reactor in the world's highest neutron flux. The chemical separation of the berkelium from the targets that were irradiated in HIFER uh, took almost 6 months, um, with the purification up to 1 part in 10 to the 7. This was performed at the Radiochemical Engineering Development Center uh, in Oak Ridge, behind 3 feet of concrete. Heavy ion irradiation with calcium-48 was done at the Fluorov laboratory in Dubna, Russia, and that required 150 days of continuous irradiation at the world's most intense uh, calcium-48 beam. And so you see at the left there a picture of the cyclotron at uh, in Russia, and at the right there a picture of the berkelium. It's the green dot at the end of that of that test tube, and that was what was shipped to Russia for this experiment. So what we did with element 117 is we established a beachhead on the island of stability. And so we now are addressing a number of key questions. Where does the periodic table end? Does the periodic law continue for the heaviest elements? What is the limit of the number of protons and neutrons uh, that a nucleus can contain? Do superheavy elements have special nuclear and chemical properties? And does the island of stability exist? Well, the element 117 experiment helped answer that last question by establishing that we are at the shore of the island. And we can do this by looking at the isotopes of element 113 nihonium that have been created, including at the far right, the element that was a decay product of the element 117 experiment. So you can see that there have been 5 isotopes of 113 created to date, spanning uh, uh, spanning 8 neutron numbers. And so we have been able to add 8 neutrons to element 113 in these experiments. In adding those 8 neutrons, the lifetime of the created nuclei has increased by a factor of 7,000. So now we have to ask, we're about 7 or 8 neutrons from the center of the proposed island of stability. What happens if we can get there, and what will the lifetimes be? And that's actually what we're trying to do, is to fill out the chart so we have a better idea of the impact of these shells and what these lifetimes might be. So the discovery of Tennessine has advanced our understanding of superheavy elements. It also included the discovery of element 115, a decay product of Tennessine. And so including promethium, 3 chemical elements are credited to Oricl, and a total of 9 elements have been discovered using Oricl isotopes. These discoveries also include 11 new heaviest known isotopes, which show a general trend toward increased stability with increasing neutron number. So this shows the critical role of nuclear shells. It provides experimental verification for the island of stability, and it could never have been accomplished without international uh, without international cooperation. We could not have done it alone because at the time we did not have the accelerators that could do it. Russia could not have done it alone because at the time they could not make the targets. It's interesting that, when you discover a new element, it creates a stir in the press as well. People can understand that. And actually, it's in case of element 117, element 117 decay chains appeared on The Big Bang Theory, season 9, episode 3, and you can see Amy there, and to her uh, uh, to the right of that figure is an actual element 117 decay chain that was written on that whiteboard. They never said anything about it, but it was there and somebody saw it. The element 117 discovery was also uh, one of the top 10 science discoveries of that year, and it was featured on the cover of Physical Review letters. So as we go into new elements, as we've discussed, element we can no longer use calcium-48 beams. And the chart at the right here shows calculations of how the cross sections might decrease. Currently, for the experiments that we have been talking about, we have used calcium-48. The next available ion beam for creating super heavy elements is 50 titanium. And you can see the cross sections go down by about a factor of 10. And then as you go on to the next possible beams, they go down for a factor of 10 and more. So we're going to have to do at least a factor of 10 better in the next experiments as we look toward Z equals 119 and 120. You can do this with heavier targets like Einsteinium, but we cannot make enough Einsteinium. And the lifetime of Einsteinium is too short to be convenient for a super heavy element experiment. So the key is going to be making increased amounts of heavy actinide targets. And this is something that we can do, but at the levels of factors of 3, not factors of 10. It will also require new and upgraded accelerators and ion sources because we need to deliver higher beam currents. The cross sections beyond 118 are just getting too low, so we're getting back into the 1 atom per year problem. Experiments will also require very high doses, and reaching these doses in a reasonable time will require higher beam currents, leading to higher damage rates. We're going to need the current experiments were done with beams of 1 particle microamp and lower. We're going to have at least 3 times that, possibly 10 times that. So new target technology may be needed. It's taken a decade, but these higher currents are becoming available at in Russia and in at the Riken uh, Accelerator Lab in Japan. You see at the right the new super heavy element factory at Dubna in Russia, which was built for this purpose. At the same time, mod uh, upgrades at Berkeley and at the Institute of Modern Physics in China uh, have allowed them to enter this super heavy uh, element research ac activity. So now there are programs going on in Russia, uh, at Riken in Japan, at the Institute for Modern Physics in China, and at Berkeley. So this is a, a, a nuclear chart showing the progress that has been made to date. And so going vertically, we have proton number. Going horizontally, we have neutron number. The green area are the areas that have been explored by the current research. The yellow boxes indicate additional isotopes that we know how to make and could make relatively easily. The blue boxes are the focus of the activity now, where we are using titanium and vanadium beams to look for elements 119 and 120. And the light tan boxes are where we would like to go, but we don't know quite how to get there because it involves uh, uh, beams that we don't with cross sections that are too low for current technology, uh, but it does show the path to get all the way up to n equals 184, which would be the center of the island. So in summary, super heavy elements offer unique research opportunities, 6 new elements since 2000. Extreme numbers of protons, neutrons, and electrons may lead to novel properties, and this may be the most interesting part here. If we can utilize the island of stability uh, to create these new elements with longer lifetimes, this will enable chemistry and material science. And we have no idea what the properties of these atoms with extreme numbers of protons, neutrons, and electrons might be. Continued progress depends on availability of actinide targets, higher current ion beams, and new and upgraded accelerators. Elements 119 and 120 will start a new row of the periodic table, and so we're on a journey to create these new elements, and we believe we have a reasonable chance over the next several years to observe both element 119 and 120. And so here is the current periodic chart. You can see where Tennessine is in the lower right corner in blue. the new elements 119 and 120, if they were successfully created, would go right below francium uh, to the left of the at, at the left end of the upper chart there. So you can see the red column ending in francium, and 119 would go right under there, and 120 would go right next to it, and that would start the eighth row of the periodic table. So with that, thank you, and I'd be pleased to answer any questions.
All right. Let me get this, get my mouse moving here and wait just a minute. I'll go up here and do dynamic gallery. All right. Any questions from anyone? Just mute yourself and ask away. And I will make a couple of comments and questions. Jim, you mentioned way back early in the presentation that that old periodic table that you showed still exists, and it does. It's in beta 3 at Y12, and it will be preserved as a part of the Manhattan Project National Historical Park. So we have that historical element uh, still in existence there. Now, let me ask a question that's probably going to show my ignorance, but that's all right too. These elements that are being discovered only last or only exist for very short periods of time. What is the value of having those elements that only exist for a very short period of time?
Okay, so that's a very good question. And at this stage, it's primarily scientific value. And this brings in the importance of the island of stability. So those elements probably wouldn't exist if we didn't have the nuclear shell structure, which made the super heavy elements have longer half-lives. Now we are 8 neutrons away from the double closed shell. If we can get to the double closed shell, those lifetimes might be years.
Ah,
And so that's really the the breakthrough. Because if we have longer lifetimes, even in minutes, you have enough time to study the chemistry and the and the physics of new elements with extreme numbers of protons and neutrons. And this is going to reveal new science.
hmm. Okay, thank you for that. Now, the interesting fact that only two elements have been named for individuals. Uh, and I'm really glad that we've got Tennessine included. Can you talk a little bit about, you've mentioned what's happening in Russia and what's happening in the U.S. Can now realize Japan is a little bit on my radar right now because I'm just returning from a trip there and I had a wonderful time in Naka seeing the tokamak that's there. But tell me about that RIKIN. Is that something like the National Laboratory here?
So
Or
that's yes, that's one of the national laboratories in Japan,
yeah.
and they have a world-class accelerator facility there that actually was the site of Japan's first cyclotron
Okay.
back before World War II.
Oh.
And if you look at a picture of it, it looks very much like the cyclotron that was at Berkeley at that time. And
Oh.
it, and in fact, uh, they could have done all the experiments that were done at Berkeley to discover the transuranics uh, if if they had won the war. And because we won the war, the U.S. Army went in and took that accelerator and dumped it in Tokyo Bay. And so it has taken them this long to recover, but they have a good chance. Russia also has a good chance. Uh, Russia, uh, the team at Dubna with Oganesyan, uh, at the time the only accelerator in the world that could have done the 117 experiment. Uh, we had a very good uh, uh, productive relationship with them. And we participated in the experiments in Russia, and we were involved scientifically as well as with targets. But of course, the Ukraine war interrupted that. And so that cooperation is kind of on hold now. Had it continued, we might have already been at 119 and 120. But of course, it did not. The so 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 that's a, there's a very interesting story there. I mean, we showed a picture of the super heavy element factory that was built at Dubna in Russia, which is a major commitment to this field. Uh, the cyclotron magnet for that factory was constructed in Ukraine,
Hmm.
and it was because they had the heavy machining capability to do it. And so this was just before the beginning of the war, when there were all the skirmishes and intrusions along the Russia-Ukraine border. And somehow they were able to ship it from Ukraine to to Dubna in Russia during that period.
Hmm.
And so, had the border was basically closed, but they figured out a way to get it through. Had that not happened, then Russia wouldn't have the super heavy element factory. So there's a lot of intersection of of uh, world affairs and and the scientists and their labs in this work.
So right now, you mentioned that it's on hold, the relationship between the Russian uh, facility and U.S. or Japan. So there's no
Yeah,
progress
and
being made.
no, so there is progress being made with
Okay.
Japan. Of course, they have upgraded all of their accelerated capabilities at Riken, and we are on that team.
Uh,
And we traveled to Japan, and they are working on element 119 right now, and we're part of that. And it's a very long experiment because it takes years. Uh, and even if you have good beam currents, you don't know what energy. And so there's a lot of pre-work that has to be done to pick the right energy, because you don't want to run an experiment for a year at the wrong energy and learn nothing. So that's very healthy, and that's working. Uh, what the Russians have done is they have upgraded the capability of their high flux reactor to make berkelium, and so they have made berkelium, in the last 10 or 15 years, and they are in the process of starting an experiment for 119 using a titanium beam and a berkelium target. That experiment could have been done with our partnership 15 years ago.
Oh my goodness. It's amazing these international relations that are taking place to move these experiments along. And it's good that the US is involved in it, but we can't do it alone, is what I hear you saying.
I think that's true in a lot of areas of science. I mean, think CERN, for example. That's a classic example of something that needed major partnerships across the Europe and the US and Japan in order to make it work.
Hmm. And
And think ITER as well.
I was just going to say, ITER is another good example of that. And of course, you've been to that facility in Naka, Japan,
Yes,
and it's amazing to me that they really like ITER and they talk a lot about it. So they understand our relationship quite well
right.
and I think are making good progress on fusion research there.
Yes, that's a very a very important part of a very long journey
Yes.
to create a burning plasma.
I've said often that fusion energy has been 30 years away all of my career. I believe it's still 30 years
I
away.
think you are right, but it's a closer 30 years than it
Yeah,
was 30 years ago.
I think that's true. Well, okay, someone else come up with a question for Jim. This don't let it just be me talking with him. If you've got a question, just unmute yourself and ask away.
Hey Jim, this is Richard
Hi,
Smith.
Richard.
Hey, how are you?
Good.
Hey, I found your discussion of the science and the physics real interesting here. I wanted to follow up on the international relationships because I know you've been involved with it for a long time. Is there a story behind how the U.S. and Russia came together to go down this path and and discover 117 or has there been collaboration all through the years after the Cold War?
Well, in the super heavy field, actually, the collaboration began uh, with, probably with element 114, 114 because at the time when they were using uh, the hot fusion process that was developed in Russia and using the Russian accelerator, uh, they reached out uh, to Livermore for help with the detection of the new elements because they needed new capabilities in that area, and we actually worked with them. They were using Oak Ridge targets, but they were collaborating with Livermore on the actual experiments, and the Livermore people, some of the Livermore people were co-authors on some of those discoveries. When it came to element 117, there was just those were using kind of legacy isotopes that didn't have to be produced directly. Berkelium has a lifetime of less than a year, so you have limited time after you make it to use it. So it has to be made fresh. And so they actually skipped 117 and went all the way to 118. And then uh, there was a lot of discussion between Oak Ridge and Russia about how to how how to share a 17 a Berkeley target for the 117 experiment, and that actually resulted in a formal cooperation between Russia and and Oak Ridge, in which we uh, joined the collaboration, and we agreed to provide the target if they would provide the beam. And so we worked together on that. And so that's kind of the history. So there was some there was uh, interesting work between the U.S. and Russia that led to all of the most recent super heavy element discoveries.
When did that collaboration begin?
Well, for the U.S., I mean, for Oak Ridge and Dubna, it began at a at a lunch that I had with Ognessen in 2008. And that is
Excellent.
when the agreement was made
Yeah.
about how the experiment would go, who would participate, and what the timing would be. And it was very, very critical because everything had to work.
Yeah.
The berkelium had to be shipped to Russia quickly. They had to be ready to run for 150 straight days, tw 24 hours a day. Uh, if there had been interruptions in the work at Haifa or interruptions in the work in Dubna, it would have been very difficult to pull this off. And it's quite interesting that shipping the berkelium to Russia turned out to be very complicated because uh, it was actually shipped on a commercial aircraft, following the rules. But the first shipment was refused in Russia because uh, there was some problem with the paperwork that Delta had filled out. So it was shipped back. And of course, now you have, it's decaying while you're doing this. Uh, and then the second shipment was refused because uh, during the time between the first and the second shipment, the rules for accepting that material had changed in Russia. And so our berkelium crossed the Atlantic 5 times before we wound up
Whoa.
in 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 Russia. Fortunately, that was done relatively quickly, so it did not impact the experiment.
5 times. Okay. Richard, you have any other questions or anyone else have any questions?
No, I'm fine. Thank you.
I appreciate you asking that question. Anyone else have a question for Jim? Well, Jim, thank you very much for making the presentation and being with us today. And we will. I want to ask a quick question before we end. I'm going to have another guest on later that's going to talk about Germany's nuclear program. What do you know about, you mentioned the cyclotron that was in Tokyo. What do you know about Japan's effort during World War II to produce an atomic bomb?
So all of the major countries understood the significance of the discovery of fission.
Yes.
And so they all knew uh, and had the ability to write their equivalent of the Einstein letter.
Yeah.
I don't know if that happened in Japan, but they understood it and they had a program too.
Yes. I,
As you know, the Germans chose the wrong path,
yes.
and that held them up. Uh, I don't know. I don't know. I don't think that the Japanese understood they were working on it. I don't think that they gave it as much priority
Uh,
as the Germans did.
yeah.
Uh, so I don't know I believe I don't know that cyclotron was built because they thought it could help them get to a bomb. I think it was built for science.
Ah, okay.
And,
That's
and uh, but I think they did have discussions in Japan about this possibility. And of course, the engineering involved and the huge production capability that is needed, as you see at Y12 and K25 and X10. Uh, I mean, that may have been beyond them, that they just didn't want to dedicate that amount of effort to it.
I have one book. There are others, but that talk about the Japanese bomb. So there, there's all kinds of information being made available now that has not been available earlier that gives some thought to just how far along the Japanese were and just how far along the Germans were. And I don't have anyone that can give me insight into Japan, but we will have Todd Ryder on again to talk about some
Great.
additional information about the German program. Okay, we're out of time now. Thank you, Jim, again, and thank you all of the rest of you for joining. I have recorded this and I will post it on YouTube and send the link out once we get it up. Thank you
And,
all very
and thank
much.
you, Ray, and all of you who joined.